Hi, this is Dr. S.P. Arsa from Mechanical and Engineering Department, IIT Roorkee. In the course of vibration control, we are discussing about the principles of passive vibration control. So, in the previous lecture, we discussed about the basics of absorber, or we can say the isolator. And we know that when the vibrations are being generated from the source or it is being transmitted through the path, and when it is like approaching to the receiver, we can certainly optimize that which method or which way is the fruitful thing, either to reduce the vibration at the source itself or to deviate the path of the vibration waves or the sound waves or the vibration through this the entire the molecular feature, or else we can straightway reduce the vibration at the receiver end. And in this particular isolator, which we are saying the passive vibration control, the isolator can be designed in such a way that it can be act as not only like the spring feature, but also the damping feature. So, when we are talking about such features, means the elastomers we can say, in which not only we have the viscosity but we have the spring features together, and they are one of the best suited material nowadays, because we can straightway adopt such kind of materials in designing of our various components in the vehicles and even the industrial machines in which the rotations are there. So, in general, when we are talking about the passive device, that means you see here we need to put some kind of, we need to add some kind of the additive features in terms of the spring, in terms of the viscosity, or in terms of the mass. Again, we need to check it out that what kind of the exciting frequencies are there from the system, or when the exciting the forces are there, then what exactly the amplitude of the vibration and the exciting frequencies from the system. Accordingly, we can choose the best suited part, like we can simply adopt the mass or spring. The damping is one of the important phenomena when we know that the high amount of energy is being created, or the high excitations are there at the time of resonance. So, we know that the mass, by adding the mass we can suppress the vibration, or by adding the spring we can control the low frequency vibration. So, accordingly we can adopt those things, and even as I told you that the elastomers which are being there nowadays, they can be even provided a integrated effect of the spring as well as the damping. So, we discussed some of the cases there itself, that how absorber can be applied straightway and what exactly the best suited methods for that. And even some of the numerical features in which you see we discussed about that, how the transmission, the transmissibility ratio or the transmission feature can be immediately just put under the suppression by adopting a proper isolation at the natural frequency or before or after the resonant condition. So, in this case now, in which we are going to discuss about the principles of this passive vibration controller, this chapter mainly deals with the design of absorber, in which you see here when we are talking about the absorber, that means you see here again we need to go with the passive device as discussed, in which we need to attach or we need to add that kind of structure which can immediately suppress the vibration by absorbing or by dissipating the energy. So, we know that when there is a dissipation, the energy is being dissipated by the two ways, one the kinetic energy and the strain energy. So, when we are just designing the vibration absorber, we need to take care that when the dissipation is occur in these two forms of energy, it is then being converted into the heat. So, our this vibration absorber should not be affected by this heat generation during the dissipation feature. So, such device which are being acted as the vibration absorber and we are adding to the main source are made up of the mass, spring and the dampers, and from the control point of view we need to see the vibration absorber can be considered as the passive controller. Passive means we can say it is a pretty normal term, just that you see the controller can be constructed using all three features, either the mass or the spring or the damper itself. So, such controller in these cases, the one of the important phenomena is the stability is not an issue there, because we know that when we are just applying the passive vibration control features, the closed loop system is like one of the basic feature of the passive vibration. So, vibration absorber are devices attached to the flexible structure in order to minimize the vibration amplitude at a specific points or a specific set of features. So, we can say that when we are just like striking a localized region of the machine or an object, we can say these passive structures which are being added there are an effective like we can say the system through which we can at least suppress or absorb the energy of the vibration. So, design of this vibration absorber has a long history actually, somewhere starting in the early 19th century by the Den Hartog. Even he introduced that the Faham, which was like one of the scientists, he simply says that why can't we adopt those things to suppress that, and in which you see here he simply assumed a second mass spring device which simply attached to the main devices. And in this like the model in which you see already there was a system and the mass and spring is to be attached there, it simply prevents it from the vibrating as the frequency of the sinusoidal forcing part from the main device. So, like this mass spring is simply like putting to eliminate whatever the vibration features or the transmission is coming from the machine to the other parts of that. So, if the absorber is tuned, that is one of the specific property, if this absorber is exactly tuned so that its natural frequency coincide with the frequency of the external forcing, the steady state vibration amplitude of the main device becomes almost 0, because then entire energy is being gone to the absorber, because now it is tuned with the entire system's frequency. So, when we are thinking from the controls perspective, the absorber acts like a controller that has an internal model of the disturbance, which therefore cancels the effect of the disturbance outside. So, this is one of the basic mechanism which is working from the absorber to the device, because we know that whatever the internal disturbances are there, and through these internal disturbances, when the resonant conditions are being appeared, it is clearly absorbed the entire amount of the energy which is being there or which is being transferred from the main device. So, the vibrating system generally consists of the mass linked to the structure by the spring and a damper, and the vibration absorber are just set up in such a way that the mass can vibrate at a specific frequency just close to the main structure, which I am going to show you in the next slide. So, when the structure starts to move under the excitation, the mass of vibration absorber also move with the same structure, and this creates a new system with a different behavior. So, as you can see that when like the entire absorber is being you see now like covered the mass and spring, and then you see when it is attached to the basic system, even whatever the forcing frequencies are there like f sin omega t or cos omega t, whatever you see, then it is straightway going towards the absorber part, which consists the mass and spring together, the undamped system. So, whatever you see like the frequency which is being there from the exciting system, and it is attached like it is going towards the attached absorber mass, and when they are tuned to itself, the entire energy is being absorbed by the absorber mass. So, it is then impossible to reach an uncomfortable acceleration within the structure alone. So, this is the basic concept of vibration absorber, which is then attached to the basic structure. So, when we are saying that when there is in the main machine or the main part you see here, or the entire component the vibrating mass which is under sinusoidal force, say f0 sin omega t, acting on that like the undamped system in which the mass and spring is there. So, we can say that when the forcing frequency equals to the natural frequency of the main mass where the force is being exerted, the response is infinite because of the resonant feature. And when like these situations are coming, we know that the severe vibrations are being occurred in that. So, when we are adding the mass on the system just to reduce the effect of this vibration, at the same like we can say the excitation forces, then this particular mass through this like whatever the attachment is there through the spring is clearly absorbing the entire energy according to the Newton's second law, which says that if a mass of the system is increased while the force is while force input is same, then certainly you see the acceleration will decrease according to the second law, where you see the rate of change of momentum is giving the mass, and mass is nothing but equals to the force is nothing but equals to the mass into acceleration. So, we know that we are not changing the mass in one point of time when the force is being acting and whatever the excitation is coming, but on the other hand with the same force when we are simply adding the mass, certainly the acceleration should be reduced. So, when such things are there, we can straightaway use this thing with the increase of mass feature. So, when absorbing mass spring system is attached to the main mass, then we can see that the resonance of absorber is absolutely tuned with the main mass, and the motion of main mass is almost reaching to the 0 at the resonant frequency. That means, whatever the energy or the excitation amplitude is being created or induced at the resonant condition, it is absolutely absorbed by the attached spring and mass. And the energy of the main mass is apparently, we can say that this absorbed feature at the tuned dynamic absorber. So, this is one of the interesting phenomena in the motion of the absorber, and we can say that at the resonant frequency these absorber are just showing their finite behavior under the steady state feature in absorbing the entire energy. And it is so, why? Because we know that when the system is just changed from 1 degree of freedom when the single mass is there to 2 degree of freedom when the mass and spring is being attached. So, now you see here we can say that the two resonant frequencies are there, and both the frequencies which are being, we can say that neither of which is equal to the original resonance there. So, certainly you see here when there is a shift in the frequency, the resonant feature of the entire system which is being converted from single degree to 2 degree is just gone down. So, this is the basic physics in the vibration, says that when something is being added as a mass and even that is tuned to the basic system, certainly you see here the system entire frequency is being shifted as per the Newton's second law. So, this approach to vibration control is especially useful when the equipment has inherent high vibration, or we can say when it has the transient feature due to any impulsive or impactive forces, like we can say that the diesel engine, the hammer mills, the positive displacement pumps like you see reciprocating or centrifugal pumps. So, in such kind of devices in which you see they have the inherent nature because of their rotation and other components, we need to add these kind of masses just to shift the frequency and to control the entire vibration by tuning the additional mass. But with the low natural frequency isolation, when we are just trying that, you see the system is just exciting at the low frequency, this isolation requires a large deflection isolator such as the soft spring. And the soft spring can be used to control the vibration, and which can then lead to some rocking motion, which are somewhat you see because ultimately that energy has to exchange. So, that is not sometimes acceptable. So, we can say that an inertia block which is mounting on a proper isolator can be effectively used to limit the motion, and then can be provided a simple solution to the vibration isolation. So, inertia block are always being useful in the application where system is composing a number of pieces of the equipment, and they are just continuously supporting to the entire system for vibration generation, and even in the transmission they are continuously playing their key role. So, just like we are saying that one example in which we have various these things are there, and we just want these things means these small we can say the masses are there, and it is in just in the settled in the continuous way. So, inertia block needs to be put because they lower the center of gravity, and once they lower the center of gravity, we know that the axis of rotation and the inertia the moment of inertia axis is just trying to settle down. So, this like it is just offer towards some kind of additional feature of the stability, and they increase the mass, thus decrease the vibration amplitude, and also you see here it is decreasing the, we can say, whatever the rocking feature, the exciting feature of the entire system. And also you see here, due to this there is a minimization of the alignment errors because of this inherent stiffness of the base. So, we can say that they are also acting as the noise barrier between the floor on which they are mounted and the equipment at which you see these things are being coupled to. So, you see when we are just talking about this system in which like these isolator or the absorber are being there, and like some as an inertia block, and they are just acted as the vibration controller with the same time the stability feature, we can simply write the equation of motion with those as the mx double dot, m1 x1 double dot is the inertia force due to the vibrating mass, and the k1 x1 and k2 x1 minus x2. That means you see like this spring is being added towards, you see here like controlling the vibration with this spring, we can know that you see some kind of rocking features are there, and then this mass m2 which is being added with this with the other spring stiffness k2 which is nothing but x2 minus x1 is just for the balancing thing, the inertia blocks. So, when we are equating those like the equations in form of the force balance, we can say that these inertia blocks are just effective when they are mounted on a perfect place as the isolator, and if there is no damping in the system, then we can say that the responses of these 2 degree of freedom system is infinite at certain new frequencies, because now my system while adding this inertia block is now converting into the 2 degrees of freedom system. And also you see the system may not be a problem when the machine is running at its natural frequency, because an infinite response can also cause the problems during the startup and the shutdown. So, certainly you see here we need to check it out that how the frequencies can be shifted. So, finite amount of the damping for both the masses, for both you see here either the added or the basic mass will prevent the motion of either mass from becoming an infinite at either we can say that the previous natural frequency or any new resonant frequencies. But this is not you see the practical situation, because we know that the damping is always present in either mass spring element, then we can say that the response of the main mass will no longer be no longer be 0 at the targeted frequencies. So, the mass of the system is increased at the we can say equipment foundations by simply adding that. So, we can say that to just successfully apply this method for vibration control, the machine must be firmly connected to the foundation, and then it has to transmit the vibration in such a way that the mounting can be specially featured out. So, from the machine design perspective, the foundation that include a well designed solid plate, we can say that the epoxy growted or we can say a concrete base that will be help out to just control the excitation not only at the source and even in the propagation, and the proper maintenance can be done exactly at the looseness or the eccentricity or even the alignment feature. So, the thumb rule says that the weight of the foundation should be almost 5 times of the machine weight, so that a proper damping feature can be added, and accordingly we can adapt the absorber in between the foundation and the machine for suppression of the vibration. So, there are various other you see like the vibration control techniques are there, in which the adding of mass to change the system's natural frequency is being a pretty common part just by adding the inertia blocks to the foundation. So, this mass addition is not you see all the time is a perfect solution and can be act as a vibration absorber. So, vibration absorber is applied to the machine whose operation frequency meets its natural frequency, and then you see here like we can generally put the damper or just to shift the mass, just to shift the frequency by adding the inertia blocks. So, vibration absorber is often used with the machine which runs at the constant speed or the system with a constant exciting frequency, because because when you combine the system, just gives a narrow operating bandwidth at this part. So, this is what you see, one of the basic feature. When we are just talking about the mass spring system, we know that it is a single degree of freedom system and we have one undamped natural frequency. And when every time you see like this frequency is generating in the machine, then we can straightway adopt these vibration absorber in terms of the inertia block, put it or mounting on the system, and when these absorber are just tuned to the basic vibration system, because now we have the 2 degrees of freedom system as you can see on your screen, then certainly you see here these absorber are perfect in controlling the vibration by just shifting the frequency, and the same time the energy absorption can be like effectively done at the excitation source. And in these cases you can see the displacement. The yellow region is clearly showing that when the system is exciting at the resonant condition, the huge amount of amplitude, the energy, you see that the displacement feature is just infinite. But if we want to bring it down to 0, then you see this closed curve, this is what you see, the closed curve, it just says that whatever the added mass, the inertia block is being there, it can simply tuned, and you see whatever the energy of excitation is there is completely taken away. And then you see here like all these frequency band in which you see the excitation or vibrations are there, it can be immediately absorbed during that time. So, if you just look at from the mathematical point of view, in which you see here we are converting a single degree of freedom system to the 2 degrees of freedom system, we can say that the inertia block which is to be added to the entire system as the vibration absorber, then the equation is m10 and 0m2, x1 double dot, x2 double dot, and then you see here the stiffness matrix which should be which should be symmetric along the diagonal, then it is k1 plus k2 minus k2, and then we can say that this is what my x1 x2, and whatever the force which is being exerted on the main machine. So, it is f0 sin omega t. So, when the system is excited due to the harmonic excitation as f0 sin omega t, we know that the input function for the displacement is x1 sin omega t, and the next, which is we can say the displacement feature for the other mass is also x2 sin omega t. So, when we are trying to solve it for the natural frequency and eigenvectors, we know that we need to go and arrange the matrix in such a way that the determinant of minus omega square m plus k becomes 0, and then you see here we can simply get these equations. So, when we are talking about the eigenvectors x1 x2, then it is nothing but equals to f0 and 0, that is what my force matrix, the force matrix, and the displacement into just minus m omega square plus k plus k. So, it is k1 plus k2 minus m1 omega square minus k1 and then k2 minus m omega square inverse, or even we can say that it is equals to 1 by delta k1 plus k2 minus m omega square minus k1 and then it is k2 minus m2 omega square inverse. So, we are now trying to change in such a way that you see the f0 which is the input feature and x which we just want to see here to be just like that what is the outcome featured is there in that way. So, we can say finally the x1 x2 is nothing but equals to 1 by delta k1 plus k2 minus m omega square f0 divided by k1 f0. So, when we are trying to calculate the delta is nothing but equals to, when we are just like opening the matrices, it is k1 plus k2 minus m omega square and k2 minus m2 omega square minus k2 square. So, we have now both the modes x1 and x2. The x1 is nothing but equals to k1 plus k2 minus m omega square f0 by delta, and x2 is k2 f0 delta. So, now you see we can say that the m2 and k2 which are being the added mass and the spring, and when they are just tuned in such a way that the overall displacement is 0. So, if I am saying that the x equals to 0, it is only when omega square equals to k2 by m2. So, the motion of absorber mass is nothing but equals to, say, x of a into t is nothing but equals to minus f0 by ka sin omega t, where xa is nothing but equals to f0 by ka. Since you see, like it is just the absorbing part, so it is minus. And when we are saying that the force which is being acting on now the absorbing mass transmitted through the main masses, it is nothing but equals to ka xa equals to ka minus f0 by ka, you see here, which we are replacing, or else we can say that it is nothing but equals to minus f0. So, that means you see here the total mass is being, the total force is being transmitted to the absorbing mass, and the force provided by this m2, if we are saying that it is 0 f0, which is nothing but the disturbing forces, like when it is just being there. So, the 0 net force acting on the primary mass is just giving in such a way that the entire force is being now transferred to the added mass, and there you see the displacement x is nothing but equals to ka minus m a omega square f0 divided by now the total stiffness k plus ka minus m omega square into ka minus m a omega square minus k square. So, this is what the arrangement of the interaction of the stiffness feature of the main mass and the added mass, and then also you see here how the mass variations are there when we are just trying to compute the relative displacement. So, you see here we have the two main frequencies. One, if I am saying the main frequency, it is nothing but equals to the original, we can say the natural frequency is square root of k by m, and this primary system frequency is without the absorber. But when the absorbers are being added, then the frequency with the absorber is omega a square, which is nothing but equals to square root of ka by ma. So, you see here what we have the two frequencies omega p and omega a, and when we are just saying that there is a ratio, say mass ratio is there, which we can show by mu m a by m. When we are saying that the frequency ratio is there in between, you see the omega a and omega p, means omega absorber when the absorber and without absorber, or also we can say the ratio of frequency in between omega and omega a. Omega is the overall frequency of the system and omega is the absorber feature, absorber mass. Then we can say that the normalized displacement of the premier mass, the primary feature, you see in the like the premier feature of that, in which first mass is there without the absorber, is nothing but equals to x k divided by f0. Sometimes we are saying that this is what you see the transmission feature when you have outcome the x and f0 is the input, is nothing but equals to the modulus, the normalized feature of 1 minus r square. R is nothing but equals to the frequency ratio omega by omega a 1 minus r square divided by 1 plus mu times beta square minus r square and 1 minus r square minus mu beta square. So, this is what you see here, the normalized displacement of the primary mass when the added mass is being there as a suppression feature of the passive vibration control. So, we can conclude this, that the damping which can be reduce the resonance amplitude of the system is always applicable at the resonant feature. The amplitude at the operating point will certainly increase with the increasing at the damping feature when these things are being added. So, select the natural frequency which will be tuned to 0 amplitude. So, then you see here we need to just go that how we can select the omega, so that the amplitude whatever the things are being coming, it should be 0. So, from this relation we can say that the relation between the k2 and m2 can be straightway obtained by the omega square equals to k of a and divided by m of a. So, we can select the added mass and the the spring property added Ka in such a way that whatever the resultant amplitude is coming at the main mass could be 0. So, you see here we can say that this is what the amplification feature x of k divided by f0 and the r And you can see that when you have this x of k by f0 equals to 1, there is all the straight line in this part even when we are changing this part. But when we are changing the damping part in such a way that you see the damping is here, which we are defining Ca divided by 2 Ma omega p, that is nothing but equals to, see, like it is clearly showing that we have a clear feature of the damping, the dashpot feature Ca divided by, you see, 2 Ma omega p. So, with the variation of the zeta, you can see that there is a clear variation when you have the omega by omega r is absolutely at 1. This is, you see, like the natural frequency, there is no excitation. That means the added mass is a perfect absorber at that point, and the entire amplitude is being washed out, and you have xk of divided by 0, xk divided by f0 is almost 0 there. But when you have the frequency ratio omega by omega a, that is, you see, we are saying the r is now, you see, like just varying in such a way that, like when it is just going beyond 1.2, 1.4 or below that, and with this damping, the damping ratio zeta, which is nothing but equals to, see, which we have previously, like put here, that it is like just showing the damping ratio at the available and, like at the p part, we can say that with these features there is a huge amount of, we can say, the these amplifications are there, and this is nothing but equals to, see, just showing that whatever the absorber mass is there, it is not able to suppress the vibration at those features. So, from this, you see, here we can say that when we are just putting the damping ratio along with the added masses part, then how we can control the vibration excitation, and like in terms of, you see, like the inertia blocks, or in terms of the damping together. So, the 2 degree of freedom system, which is simply showing here as the 2 natural frequencies, just corresponding the 2 normal modes also at these frequencies. So, we can say that at the lower frequency mode, both the masses are in phase, as we discussed, and you see at higher frequency both the masses are absolutely orthogonal, or we can say out of phase there. So, when such systems are there, then it is somewhat drastic, you see here, to control the things. So, we can say that the 2 degree of freedom system, they have the normalized forcing frequencies from this when they are in phase is just 0.61, and when they are, like out phase, where you see, like the opposite modes are there, it is just crossing 1.3, as you can see. 0.67 is clearly showing here, and 1.67 when you see the things are being varied in that way. And when you see here the undamped classical tuned, like things are there, means the damping is not available at that point, then it is almost nearly equals to 1, and then you can see that when the damping ratio is ineffective, then the things are becomes almost 0 there. So, you see here in such kind of system, when we are simply adding the inertia blocks to suppress the vibration and the damping is involved there, then we need to check it out that whether the masses, because it is now the 2 degree of freedom system, whether the masses are in phase or out phase, or when the damping is not an effective part, or it is not present rather, then you see here we can say that absolutely the suppression of these vibration through this inertia block is absolutely occurred at this omega by omega a equals to 1. So, we can say that these, like the magnitude and the phases at which you see the force is being applied to the main masses are clearly shows in these part, that you see how the variations are there. And when the damping is being achieved at the same time, it is a clear reduction in the level of the vibration, or we can say that we can perform the vibration suppression at other than, you see, like omega by omega equals to 1. So, at the lower frequency, at we can say 0.667, or the higher frequency 1.3, these, you see, the damping can be also act along with the added mass. So, when we are considering the symmetric system, then we have mx double dot plus dx dot plus kx equals to 0, and when we are just adding those things, we know that the whatever the mass, the damping or the stiffness matrices can be straightway adjusted, so that the model damping ratio can get the desired value, what the requirement is there to suppress the vibration. So, we can say that it is simply providing the insight into how to adjust or to design the individual element like the mass spring or damper in such a way that we can achieve the desired damping ratio for the system. And when we are doing this, especially towards the mechanical part, then the damping in the structure is specified in terms of either a value for the loss factor due to like the stationary or non-stationary part, or the percentage of critical damping can also be just given with the damping ratio. And we can say that when we are just trying for a single degree of freedom system or 2 degrees of freedom system, the things are quite feasible along with these parametric features, mass, we can see the damping or the stiffness part. However, in many cases you see here, we know that the behavior of the given structure is not be satisfactorily modeled when we are just going with the single degree of feature. So, in such cases you see here, we need to go for higher degrees like n degree of freedom system, which is having the nth damping ratio, say zeta n, and these damping ratios are just like for all the normal modes which are being there, you see under any of the symmetricity of the matrices, the damping matrix, mass inverse matrix and the stiffness matrix which is symmetrical, is just giving all these damping ratios according to their the normal modes. So, if you are saying that if we just if you are just decoupling the motion, then the damping ratio zeta can be defined as the lambda d divided by 2 omega I. So, what we have here? We have the two features in this. One, the lambda, that is the eigenvalue, along with you see here whatever the rotational frequencies are there, and with these frequency ratios we can say that the zeta, which is nothing but the damping ratio, can be defined for the system. So, we know that the omega I, which is in the denominator, it was nothing the undamped natural frequency of the system, and the lambda I, which is also showing the eigenvalue of the matrix along with the damping. And this ratio is clearly showing the effect of the damping when we are just going in the damping ratio feature. So, when we want to formalize this, then we can say that the definition, which is just to like examine the normal modes, just to be evaluate whether the damping, inverse mass matrix and the stiffness is symmetric or not. If it is symmetric, then we can say that the damping, inverse mass matrix and K is absolutely equals to the stiffness, inverse mass and damping part. But if it is not, for any normalized case, then the damping ratio matrix can be defined, as we already discussed in that matter, just defined by the Z, and in this way you see here we need to define the Z in terms of the critical damping matrices, as we discussed in the previous lectures, D critical. So, in this case you see here where the D critical is playing a key role in defining the normal mode other than the symmetricity, we can simply define the damping ratio Z is equals to the D critical half minus half to the power minus half D into D critical minus half. So, this is what you see some kind of in the damping, it simply shows that with the critical part, the critical damping and the available damping, how you see the symmetricities are there, and then accordingly we can calculate the damping ratio. So, you see here when you have the normalized mode in the symmetric way with the damping, inverse mass and stiffness, there is no problem, we can straightway go zeta with the lambda I d divided by omega I. But if you see we want to examine the normal mode for different cases in which the symmetricity of this matrix, in which you see the damping, inverse mass and stiffness is not the symmetric way, then we need to go with the this like the damping ratio along with the critical damping. And when we are just trying to formulate this, we know that this the D critical and the D bar, which is nothing but the normalized damping matrix with the mass for any like a structure, we can simply calculate the the matrix for the damping ratio Z, and in this you see here the eigenvalues of this can be immediately find out along the diagonal of the entire Z. So, if we want to calculate the eigenvalue, this is again the Zi is nothing but equals to diagonal along the like the entire Z matrices, and it is nothing but lambda I into Z, or we can say it is sometimes the diagonal of the zeta star. The zeta star is nothing but the damping ratio for such system in which it is like we can say the ratio di divided by omega I is less than 1. That means, you see, it is for the underdamped system, and when you have the underdamped system and you want to calculate the like the damping ratio, then we need to go with the diagonal matrix of the entire Z matrix. But when the system is the symmetric, say D m inverse k is equals to k m inverse D, then certainly you see here we can simply calculate using the omega I or the lambda I d straight away. So, we can say that from this consideration, it is simply like apparent that one can bring about the reflection by incorporating an element with a different inertia from that same medium where the excitations are there. And since the element of that type are just often idealized with the rigid masses, we can say that they are simply the blocked masses. So, we can say with these like the practical application and the realization of the entire system, the block masses concept can be immediately adopted according to the seismic blocks and the added masses. So, we can say that like when we are trying to do these things, either when we are like making the added mass of the seismic masses, the construction materials, because they are more stiff, can be straightway accommodated as a steel or the concrete, and they can simply put, you see here, like on these particular path, just to provide the significant discontinuities in the medium properties by adopting a compliant element approach. And for that reason, it is much more common to use a complement than the stiff elements, and we can say that for this reason, for the structural reason, they are sometimes they are saying that we need to just go with the more stiff material than the flexible one. So, you see here these things are there, we have seismic block here, though you see this is added mass on this particular entire system which can be suppress the entire vibrations, but we need to check it out the compliant structure support, just like you see these added masses, and they are perfect and they can provide rather a better solution according to the space, and you see here just to absorb the vibration feature, the vibration excitation feature here. So, the lastly you see when we are trying to design the vibration isolators, there are a number of thumb rules in that, and these are: first, the isolator which is of the static nature, we need to check it out, the stiffness of that isolator must be chosen so low that the highest mounting resonance can fall far below the lowest intersecting, you see here whatever like this interacting feature like should be lower down, means whatever the we can say the interesting exciting frequency which are being coming on the system due to the interaction of the feature, it should be as low as the we can say like according to this stiffness feature. And the mounting positions, second, the location part, the mounting position on the foundation should be as stiff as possible, so that the robustness between the added feature can come. The point at which the machine is coupled to the isolator should also be as stiff as possible, then we can say that the coupling can be like can be done perfectly, and whatever the energy which is being dissipated during that point, the coupled feature can be immediately act as you see the absorber or the stiffener feature. So, what I mean to say that these are critical like we can say the rules for designing the vibration isolators according to the whether we are saying that like the mounting resonances are there or the excitation features are there from the machine or even the location point of view. Few more, when we are talking about you see like these exciting features, like you know like in the second case when we are talking about the mounting position, or in third case when we are just talking about the coupled feature, they are not difficult to fulfill at the lower frequency, but you see at higher frequency the internal resonances are always creating so many problems there itself within the material itself. So, the isolator should be designed in such a way that the first internal anti-resonance falls well above the highest exciting energy of the entire machine. So, like when we are designing the isolator, we need to take care that what could be the possible way to just put the anti-resonance frequencies, and you see here like when we are just coming, the entire exciting frequencies should be well far means well like higher than whatever you see the anti-resonances are there. So, this rule in practice is very difficult to follow, but if you are not trying to follow these things, then certainly you see here we can simply like calculate or measure so that the added mass or anything you see the isolator can be put in such a way that the anti-resonant part should come immediately, and you see whatever the highest excitation frequencies are there, they are just to be go ahead in that. So, you see here in like either practically or in through computations, we need to check it out that what is the feasible way out to design the best possible way of our vibration isolators. And then you see when we are talking about the isolator, it must be designed in such a way that internal resonances should not coincide with the strong component of the excitation. Otherwise, you see here in the spectrum the entire feature will come out, and you see here it may even supply the energy to make the system or to lead the system towards unstable part. So, the isolator must be designed so that its anti-resonance frequencies do not coincide with the resonant frequency of the foundation. And in addition to these rules, there are normally like number of constraints which can be adopted according to the geometry or the stability or the strength point of view of the structure. Because you see here the local feature and the operating conditions, and whatever you see like we can say the environmental features are also playing a critical role in designing of the isolators. So, if we are talking about the entire chapter, then we could easily figure out that when we are designing the absorber, there are various ways through that we can straightway adopt a best suited method, like simply like adopting a spring. Then what kind of springs are there? By adopting the damper, or it is an integrated effect of the damping and the stiffness, or even when we are just trying to bifurcate the degrees of freedom from 1 degree to 2 degree, and then you see here the corresponding shift is there in the frequency, 1 natural frequency to 2 natural frequency. And when we are tuned when we are just tuned our like the added mass, or even sometimes we are saying that the seismic mass to the exciting frequency of the main part, then we know that we can rather lead the entire vibrating system, the main mass, towards the 0 amplitude. So, these are the best possible way through which we can design our absorber according to the condition and according to like whatever the exciting features are there from the machines. So, this is all about this chapter, and in the next chapter now we would like to see that how these concepts are being applied for the principles of passive vibration control, that what kind of you see the spring alone is suitable, or a spring with the damper is suitable, just like you see in the strut of our motorbike, which you can see just like just connected the entire suspension feature from you see the like the entire frame to the wheel, and there it is you see here we have a combination of the damper and the spring. And even you see here when you are just putting you see like your when we are choosing the vehicle wheel for like the 2-wheeler or 4-wheeler or bicycle or anything, the material of the wheel itself is playing a critical role, not only from its reliability point of view when it is running or the life you see here, but also from the damping features. So, or even the like the restoring features when it is being deformed under the air compressions. So, what I mean to say that now in the next lecture we are going to discuss about the practical applications of the absorber whatever we discussed in basic or in the design absorber, we are trying to apply, and we will see that how they are being used in that practical applications. Thank you.